Welcome, everyone. I'm thrilled to have you join us today for another exciting session in our Improving Talk series about data. Today, we're diving into something truly game-changing. If you're wrestling with complex data warehousing pipelines, you're in for a treat. We're talking about transforming your data analytic platform into a modern data estate using a metadata-driven approach. Think about it. How much time do you spend managing data flows? Dozens of tasks? Hundreds? It adds up, doesn't it? What if there was a better way? A way to dramatically cut down your ETL development effort, a way to make your data pipelines cleaner and more efficient. I'm especially excited to introduce our speaker today, Mike Deal. Mike is the Director of Data Engineering and Business Intelligence at Improving. He brings over 25 years of experience using Microsoft database technologies to our discussion today. Mike is a recognized expert in Agile analytics and Microsoft Azure DevOps. His knowledge and insights have been shared at numerous prestigious events. He's spoken at regional, national, and international SQL events, including the PASS Summit in Seattle, SQL Bits in London, and various SQL Saturday events across Canada and the USA. You're in expert hands today. Mike will show you how to build powerful, streamlined pipelines in Microsoft Fabric. These aren't just any pipelines, they're driven by metadata stored in JSON files within OneLake. By the end of our session, you'll have the knowledge to slash your coding time for ETL processes. Your productivity will soar. Your colleagues will wonder how you do it all. So grab your virtual notepads, get ready to transform your approach to data management. Let's welcome Mike Deal and jump into the world of metadata-driven pipelines.
Hey, folks, thanks very much for that introduction, Daniel. Pleased to be here today. So today we're talking about pipelines in Fabric, in Microsoft Fabric, and the metadata-driven ETL patterns that we've used, and there are various industry methods that these patterns are using. As mentioned, I'm the Director of Data Engineering and Business Intelligence for Improving, and there's my LinkedIn connection. So if you want to find me on LinkedIn, that'd be great. Improving has 18 offices across North and South America. I'm from the Winnipeg office. We're one of the more recent acquisitions of the Improving team. Prior to that, Imagine at Resources was formed in 1997, and I joined in 2001. And we were acquired in 2024 by Improving. And there's lots of expertise across all of these companies, enterprises throughout here, and we have about 1,800 employees now that we've joined with all these other companies. So Improving does platform engineering, lots of AI and ML type work, modern data, which is my practice, application modernization, business agility, like business workflows and workflow automation, modern collaboration and business process transformation. So that's usually takes the form of agile and lean things, as well as product delivery. So we have lots of expertise in those kinds of things. Plus, we are partners with the big cloud players, and the other important players as well. So Microsoft, Google Cloud, and AWS. We have really deep expertise with SAP, Databricks, OpenAI, Snowflake, Confluent, and HashiCorp. So we bring a lot of deep expertise in those things. So if those hit for you, then feel free to contact us and see if we can help you. So why would we want to use metadata for Fabric pipelines? The primary reason why we use metadata, or why I use metadata, is to reduce my ETL development and increase velocity of that development. So especially compared to SSIS, where things were very fixed. There's probably another question I should have had on here. If you're using SSIS, you might have heard of a tool called BIML, BIML, which was like an expression language that would dynamically generate SSIS packages. That was usually done at build time or release time or development time, and you had very fixed things. So we're going to see some of the comparisons to SSIS later on. Data Factory for me was a fairly big change. And I initially took some of my SSIS practices and, kind of knowledge and ways I did things and brought them to the table when I was building Data Factory. And that actually didn't feel quite right. And then I went to a session at the past summit, probably, well, just after Data Factory came out. This was pre-pandemic, and it was a presentation on using metadata for a Data Factory, and said, that feels a lot better. And there was a few other sort of aha moments I had with Data Factory. So now I've looked at this same pattern and to see how would I implement it in Fabric pipelines, which to me feel like a very natural progression of Data Factory pipelines, but implemented in Fabric. So the other thing about Fabric pipelines is that if your target is Lakehouse tables, then you have a lot better support for schema evolution without a lot of strict typing. So when I was using Data Factory, and my target was going into a SQL database, I would have to have some pretty strong schema specifications for the tables that I was targeting. So I had a database project as part of the efforts that I would be doing for supporting Data Factory. In Fabric pipelines, I find I don't need a database project to support the kind of schema things that I want to do. So the scenario that I'm just describing today is using the target of a lakehouse in OneLake. And it's like a star schema design, typical for an analytics store, data store, or a data source for, say, Power BI, or data science experiments and things like that. And the typical metadata-driven approach is driven by a set of tasks, where we get that set of tasks from some storage location. And then for each of those tasks, we have a typical pattern of loading data and merging it, or loading all data and just overwriting it, or loading some data into a staging area and merging it into a target, which is more of an incremental thing. In this mechanism, you can also specify the way you want your dependencies to run. You may, in previous with SQL databases, and I want to use surrogate keys, for example, then it would be important for me to use to load my dimensions first, and then facts that depend on that dimension. In a lakehouse architecture, I'm not using as much surrogate keys, so the order of these things is a little bit less important. But I might want to organize the dependencies into sort of bronze tasks, silver tasks, and gold tasks. At a high level. The pipelines that I would create would be based, specific to a data source type. So I might have a pipeline for loading from SQL Server. I might have a pipeline for loading from Oracle, and then, or I might have a pipeline for loading from a certain file source. So the pipelines themselves are fairly abstract. And they are driven by this metadata. But some of the abstractions, there are ways of parameterizing the type of data source that you are using, but it's in this case, that level of abstraction is probably not worth it. So just a little bit of terminology. When we talk about a data warehouse, my definition of that is that it's usually a relational database system. So Azure SQL or Azure Synapse, dedicated pool, or some other type of structured database like that. And that's been the historical mechanism for storing these analytical star schema warehouses of data. Very structured. It's great for BI. It can get expensive because it's fairly compute bound, and the scaling of compute and storage is relatively linear, and it becomes quite expensive with larger data sets. And in cloud resources or cloud systems in general, compute is one of the most expensive resources, and storage is one of the least expensive resources. So moving to the second data lake here. Data lakes are just simply cloud-based file systems, for lack of a better term, or blob storage systems. They store blobs or files of a sort. And those files can be structured or unstructured. And they can be things like JSON or XML or CSV, or more structured like Parquet files or whatever. And generally, data lakes don't have any kind of query engine on top of them. There's some separate mechanism for the querying of those file systems. So actually parsing the CSVs, for example, and answering a question of that would be like a map type implementation. So data lakes are generally really quite inexpensive, several orders of magnitude cheaper than compute, even at long durations. So if we combine those two together, then we have what's called a lakehouse architecture. And we have both structured and unstructured data in one place. It's generally really fast. And I'm going to talk about the Delta Lake implementation that is shared by Databricks as well as OneLake Lakehouse. And that is a very fast querying file-based system that has an engine on top of it that would perform the querying in a SQL-like manner. And so it is combines the best of both worlds for scaling your compute, maintaining and storing your data in a very cheap mechanism. So it's very fast. So here is the Delta table format that is used by OneLake Lakehouse tables. And this is shared by, it's an open source system. Delta is an open source system, and same as Databricks, the way it implements it. There is a folder of files that are Parquet files, and then there is a subfolder of transaction log files, which are essentially JSON files. And Parquet files are an open format that each Parquet file is a compressed column store database. Column store databases are they're very different from a relational table storage mechanism where everything is stored at the row level. In a column store database, the columns are stored, so all of the distinct values of a single column for all the rows of that column are stored in a compressed format. And so the distinct values of that are stored, and then a map to which rows those values are present in is part of that Parquet file. This is very similar to the Vertipack engine in Power BI. It's the same kind of mechanism. And in the biggest difference, I suppose, is that the Vertipack engine generally has all of this in memory, whereas the Parquet files are actually persistent. So Parquet also have their own schema definitions in them. So what columns are in this Parquet file and what their data types are. So they can be queried very fast. They can be loaded into memory quite nicely and queried very fast. And because each Parquet file has their own schema, then schema evolution is just a matter of reading the schema of each of the Parquet files. And the transaction log, these JSON files, show the history of these Parquet files and which got added when and which ones should be removed. So the files are no longer referenced when they're removed. They're not actually removed, but they will accumulate over time. These previously removed Parquet files will be accumulating, and then the optimize or the vacuum process will go ahead and clean up all those old files. They can also become splintered or fragmented, or small files, and Parquet files tend to be nice if they're a little bit on the larger size, maybe in the megabyte scale, as opposed to the kilobyte scale of file size. So the optimize process will go through and coalesce smaller Parquet files into larger Parquet files that are generally query better. So with Parquet and Delta in particular, it's easier and faster to drop and overwrite rows than it is to update rows, because updating rows will modify existing Parquet files and maybe split them, and so on. So it's better to drop the rows and replace the rows than to try and detect changes and update them, which was so when I was dealing with a relational database, like a SQL table, I would do things like checking to see, has the row changed that I'm loading from source to the data warehouse? And if it hasn't changed, don't try to update it. Just that would do things like minimize impact on the transaction log, was a better approach for a relational table. But the Parquet files, I'm not taking that same philosophy. And it tends to be a lot faster to just delete from the rows that are in the table that should be replaced and insert the new, regardless of whether they've changed. So I just got a little viewer discretion advisory warning here about there's some screenshots that are coming up that might be disturbing to you if you have bad memories of SSIS development, which I do have some of these in my past. So just wanted to forewarn you. So here is some SSIS development screenshots that where I'm calling a number of other pipelines or packages at the top level. And SSIS, I had to build things where we were developing at the column level, and all of the column metadata was very important to SSIS packages. So there was a lot of column metadata in these packages. And if there was any column changes made on either the source side or the target side, then I would have to make changes and redeploy the packages. So you would get something like that, where you would see the big red X for a particular data flow. Something in there has changed, either the source query or the target table that we were loading to. And then you would go inside and maybe update that one, and you would see, and of course, the other thing that you could commonly do is it would refresh the metadata, but then you would forget to actually map the source column to the target column. The warning would go away, but you still didn't actually map. You would see at the bottom of this, there would be unmapped columns. So you could get rid of the error, but you didn't actually map any columns to the new columns that were, or new between the source and the target. That was something you had to go and fix. And BIML was an attempt to kind of generate these things dynamically at development time. I have done projects using BIML, and it was fairly successful at that, but it required, some developer knowledge to do that. And it still didn't get away from having to deploy the updated packages. In my practice, we try to be agile, and there's a great book by Ken Collier called Agile Analytics, where he describes the approach to using how you could implement the agile lifecycle with analytics projects, data warehouses, and so on. And so that was one of those career-changing books that I read probably 10 years ago. And so being agile means responding to your customers' needs as much as possible and as quickly as possible, right? So if they want a new column in an existing attribute or some new data coming from their system to get into their data analytics, into their Power BI environment, for example, I'd want to try to be as responsive as possible to that and be able to. So I did a bunch of things for DevOps to make sure I'm automating things, but this approach actually removes a lot of coding changes for responding to these kinds of customer needs. So if a customer came to me and said, I need new data from a new source, well, In SSIS, I'd create a new data connection and a new package, or maybe a new data flow in an existing package, and I'd deploy that. Right? In this case, it's pretty much the same for Fabric. I have a new service connection, a new pipeline, and some new metadata files. But all of these the next one, new data from an existing source, same story for SSIS. I'd have to update the SSIS packages, and I'd have to redeploy. In the Fabric scenario, all I have to do is add some metadata files that we're going to look at in a few minutes. If I had a change or an addition or a dropping of a column in an existing source, then I'd have to go into SSIS, refresh the column metadata, and deploy. In the Fabric case, all I have to do is update the metadata files, and the pipeline will get that new metadata the next time it runs. If I have a changing of a dependency, I'd have to update the package and redeploy. And in Fabric, it's mostly updating the metadata files and maybe updating the pipeline. And stopping loading existing data, I'd have to remove or disable a package and deploy. And in the Fabric case, I just have to update the task metadata files, and we're good to go. So a lot less deployment required for when you're using a metadata-driven approach, and a lot less development of the pipelines once you build these fairly abstract pipelines. When I brought my SSIS mentality to running in Data Factory and now in Fabric pipelines, one of the aha moments that I had was understanding how variables and parameters could be used in pipelines. So until that, so parameters and variables are really great at providing some abstractions for your pipelines, so that these values can be dynamically assigned at runtime. So here are the three parameters that I've got for a pipeline. When a pipeline gets executed, it'll have to be given these three parameter values. And then in my designer, my tool designer, there's lots of places where I have that blue link to add dynamic content. And it brings up the pipeline expression builder, which I can either write my code myself up there, or use a lot of the prompting that's at the bottom to put values in there and give me helpful syntax. So there's quite a lot of expression language here that is available in the function side, and we have system variables and the parameters and other variables available from the bottom. So it's really easy to use these. And so then I can bind a dynamic value from using this expression builder to that particular text box or runtime. So this was kind of the game changer feature that I could use to make these things much more abstract. So there's been some changes between Azure Data Factory and Fabric pipelines, and some of that has simplified things considerably. So one of the biggest changes is that Fabric pipelines don't have this concept of data sets that Data Factory does. So we would have these data sets that we could have. We would say who they're connected to, what kind of data is it. The one in the background is a CSV. And does it have column level schema in it? And these data sets could have parameters as well. But in the new case with so then when we specified a data set, then we could give it parameters, and it would show us the map back through that data set. But the Fabric one looks quite a bit different. We have a connection on when we're rather than a data set. So we're connecting directly in this case, to the Lakehouse, and we are specifying that we're going to the tables portion of the Lakehouse, and then we can specify a target schema and a target table in this case. So we don't have data sets anymore in Fabric pipelines. So here's what my typical metadata-driven pipeline looks like. I have a lookup task that goes out and gets me a collection of tasks to execute, and then I have a for each task iterates across that collection and does a standard set of things, goes out and gets the SQL query to execute, copies from the source to the lakehouse, and then if there's a notebook after that. And so here's an example of a JSON file that we'll see a little bit more that's actually stored in the lakehouse in kind of a metadata folder that I've got that gives me some metadata about where the query file is, what the target schema and table is, and what the notebook that I want to execute. Okay, so we're going to dig into these a little bit deeper now. So as I mentioned, we're going to use a lookup to get this JSON file. Other patterns that I've used where this lookup can go and call a stored procedure in my data warehouse to get me a set of tasks there. I've just used this I've changed this now to just get a JSON file, which feels more like a coding activity than a data activity in this case. I'm going to show you a pattern later on for filtering these tasks down for debugging purposes. Let's say we've got a JSON file that has 10 or 20 tasks in it, and we really want to just debug one or two of them. Then we could apply this filter, and only the for each loop would only do the filtered tasks. And then, as mentioned, we're going to, for each of those tasks, we're going to get the query, we're going to copy the data, and we're going to execute a notebook. So here's what the get tasks lookup task looks like. We're getting it from the file section of the lakehouse, and we are specifying the parameters, the task for the file path and file name. We're using pipeline parameters to do that, and we'll notice that the file format down there is JSON file format. And when we execute that, the output of this contains this value array that we see over on the right side, as well as a count of the tasks. So we're going to look at that JSON structure, that array that's in the value that parameter. Now, for each of in the for each task, we're going to apply, we're going to give it the collection of tasks. So I've got an intervening set variable in there, which basically just takes the value of that output from the get tasks and sets it to a variable called tasks. I'm going to extend that a little bit further for the filtering a little bit later on for debug purposes. That items collection on the settings of the for each then has also an option here for either sequential execution or parallel execution. I typically choose the parallel execution and clear the sequential button so that basically the tasks will get executed in parallel according to the concurrency limits that either the underlying tasks will accommodate or the current pipelines mechanisms. So I typically see, 4 concurrent tasks executing, and as each task's finished underneath there, then it will launch another task for additional things. So I tend to prefer the parallel execution. I figure that we're going to get the best execution times that way. There have been some cases where we need to throttle, and so there are some options for throttling how many sequential items that we want to execute. Now, inside the for each task, I have several task activities to run. The first one is to read the file that is referenced by the source query. So if we remember, I'm just going to switch back here to that. If we look here, there's source query for the first one says products.sql. So we're going to actually go and read in the lakehouse that products.sql file. And we're going to get that into a variable. From the file section of the demo lakehouse, we are going to give it the path, the task folder parameter path, and then the source query value for the file. And that should find that products.sql file. And then we're going to read it in as delimited text. There's a little bit of magic happening here. The magic is that we want to read that whole file, which is just in whatever language or dialect of SQL that you want. It's got carriage returns and like multiple lines and things like that. We want to read that whole thing into a singular column, single row from this delimited text. So and we don't have a header in that row. So the specifications for the settings for importing this basically looks at, we give it a very uncommon, hopefully a column and row delimiter that are not found in that as a string in that query file. So I've put some column delimiters in here that are never going to be found, and the row delimiter. And just for your information, they can't be the same values. They can't be the same ridiculous values. That's just logical sense. Ask me how I know, though. And the other checkbox I clear here is to clear the first row as header, because I don't want to have to put the header name or the name of that thing. So the question then is, what might happen, or what is the name of that one column that comes out of this lookup thing? It is just an arbitrary name given to it by the lookup task itself, and that is in that output of that one, the output.firstRow.prop0. Presumably, if you have another column that you had found, it would be prop1 and so on, right? But that's really what we're getting for that one. So on my copy task here, I'm copying from my source connection. So in this case, it's an Azure SQL database called SampleDB. I'm telling it to execute this query, and the query is going to be the contents of this single column, first row, single column of that get SQL output. So I did my first implementation of this with a Postgres database backend that I was extracting from. I could use a query tool to connect to my Postgres instance database, write some SQL and use all the Postgres nice functions and so on that are specific to Postgres. And I could just select that query and paste it into a SQL file, a text file, save it there, and it was really easy. There was no, I didn't have to do any translation of that text to be able to execute it natively here. So one of the things you could do in your queries is you could have tokens in the query. So a token, there's not really a magical thing or a structured or programmatic thing. It's just something, a pattern that could be replaced easily by a string operation. So I will do either single or double braces around, say, like it's almost like a variable name. So I might have one called current date or current time or something like that. I could use in an expression that those values would be replaced at runtime. So I'm not showing a stage here after the get SQL to do the replacements of these tokens, because in my sample project, I'm actually not using tokens. But this came up recently in a discussion, and I thought I would just add this slide in here. If you have something like a high watermark, like maybe a timestamp value from a SQL table, or a last updated date time of some sort, you could use that to load the values that to selectively get only those values that are doing that, that are after that previous high watermark. So the question then becomes, where do you get those from, and then where should they be persisted to? Presumably, after you execute this, you'll have a new high watermark that you'll want to persist. So my suggestion is that you have a separate JSON file that's maybe named the same as the SQL query that provides the value of the tokens. And you could have a more programmatic process to look at the properties in the JSON file and do replace on the of the tokens in the query file with the values that are in that JSON file. So that's a little more sophisticated mechanism for handling tokens and that or dynamic values that you might want to know. I also maintain that the target environment, be it the Lakehouse or a SQL data warehouse or something like that, that has been loaded, is the place to store that those dynamic values. So that if you have a lakehouse for test purposes in a test area and a lakehouse for prod, that their high water marks are specific to those lakehouses because they know what they have been loaded, to what level they've been loaded from a source, right? So I think that's where it belongs. And I would probably recommend putting these in the file section of the lakehouse and use some naming conventions to make it obvious as to which of these belong to which tasks. On the destination side of this copy task, then, and notice also in Data Factory, they used to call this the sync page, and now it's called destination page, which is a better name in my opinion. Sync made sense from a strictly engineering perspective, but I like the term destination better, but they're the same thing. I am going to persist to the lakehouse and to the tables endpoint of the lakehouse using a schema and table name. Now I noticed there, when you create lakehouses in Fabric now, there is two options as to whether you use the old lakehouses which don't support schemas, or the new one that do support schemas, which is they stay as still in preview. My preference is to use schemas because they're great containers for organizing things in a lakehouse or in a SQL database for that matter. In this case, the advanced option here, I'm going to overwrite the target table. And that target table does not need to exist. It will get created automatically. If the target schema doesn't exist, that will generate an error. So you may need to have some notebook code to make sure that you have create or replace schema for the known schemas that you have in this project. But I really like this overwrite option because it removes a lot of schema manipulation on the target side, especially because we're talking to a lakehouse as opposed to a SQL database, which has more stricter column level requirements and specifications. This is where it's very different from SSIS. We do not have any column mapping, and this would apply in Azure Data Factory ones as well. In Azure Data Factory, if you're talking to a target database, like a SQL database, it uses a naming convention that's a case-sensitive naming match between the source column and the target column. Because we're overwriting and because this is Lakehouse, it's just the column names are just as we specified in our source query. After we have copied that data into the target table, that target table might be a staging table because it contains only part of the data that we're doing an incremental load, or maybe it's a type 2 dimension that we are versioning the main table of this. So if we're going to go and check and see, do we have a notebook to execute to run after the data has been copied into that target table? So we're doing a quick check to see, does the item contain a notebook property, and that notebook property is not empty. Then so that's the if expression. Then inside that, we are going to execute another pipeline that does some work for us that makes it a little bit simpler for us to execute the notebook. So we're going to call a notebook called execute notebook, and we're going to pass it in a parameter, which is the name of the item. Okay, so what's in that execute notebook pipeline? In that pipeline, we need to, the notebook task needs, the dropdown shows names, but under the covers, it's using the IDs of the notebooks. And so we don't have the ID of the notebook, so we're going to have to go out and get the IDs of the notebook that we are interested in. So there's a REST API call that we can execute to get all of the notebook metadata we have in the current workspace. And then we're going to filter that, and then we're going to, at that point, we have the ID. So in the REST API call, we're going to make a web call and have a REST API, a Fabric API web endpoint that has a base URL of api.fabric.microsoft.com/v1. And then the relative URL that we're calling after that is this string concatenation of workspaces, the ID of the workspace, which is the pipeline parameter called data factory, and then show me all the items in this workspace of type notebook. So that's the string that will do that. It's a simple get. We'll get a collection of all of the notebooks in the current workspace, and then we want to filter that collection to just the one that we are interested in, which is a match on the display name. So for the filter, we're setting it to the collection of the output.value collection of the activity that got all the metadata. And then we're going to limit that one to say only those items whose display name equals the parameter, the notebook name parameter that has been passed in. So we should have either 0 or 1 rows left in that collection that has been filtered. If it's 0, the next one's going to fail. The next step is going to fail. If it's 1, then we have the ID of it. So then the next, actually executing the notebook, we are specifying the workspace, which is the current workspace. We're going to execute the notebook ID, which is the output of that filter, dot value 0, the first row that it matches there, and the ID property of that. The last session tag value is just simply a string that says, that is used for cluster affinity. If there are, as Fabric will spin up clusters to execute notebooks on, it may have a pool of clusters ready, and this means that we can sort of share that pool nicely. There's, to me, I think there is some performance benefits in terms of how quickly you can get a cluster when you're doing a bunch of notebooks as parallel tasks. But this is a bit of a performance enhancer, I think, but I've only got anecdotal evidence to show that it's beneficial. So if we have, I'm going to talk about debugging tasks. So if you want to, your data factory, your tasks JSON files could have, dozens of rows in them of tasks to execute. And if you're in a debugging scenario, you might only want to do one of those or a couple of those. So I've inserted this if condition in the middle between the get tasks and the for each loop to optionally filter the output of the tasks folder. So there is a parameter of the pipeline called this source query filter, and it has a default value of this string, magic string, all with stars on both sides of it. So we're checking to see that parameter is not that value, then we have a filter that we want to apply. So then on the true side of that equation, if it's not that magic filter value, then we are going to apply the filter that is specified in that parameter and say that the source query property of the current item must start with that source query filter. So I could put sales in the query filter, and it would show me all of the tasks where the source query started with sales. If I put C, it would show me all of the tasks that would start with the letter C. It's a pretty primitive filtering mechanism, but it's generally pretty adequate for that one. And then it's going to set the tasks variable to the filtered value. If it's on the false side and there is no filter, that tasks variable is just set to the full collection. And then that task variable is then used in the next step for the for each. So how many pipelines generally will you need? Usually it's one per data source and then a main pipeline or maybe several main pipelines that would, that's where you would have schedules on or triggers of some sort on those main pipelines. And most of those pipelines would use the same pattern. In fact, sometimes I've built them. I build one pipeline that does that pattern for one data source, and then I've duplicated that pipeline and made some changes to it for a different data source, and then all the other stuff stays the same. So what does this main pipeline look like? It's basically calling the data source pipelines that that are the abstract ones. And we execute that one and send in the parameters for the name of the JSON file that we want to execute for that one. We might want to do like level 1 pipelines that load the dimensions, and then level 2 pipelines that are loading facts. And you could have additional levels based on your dependency tree, or you could have like a bronze level that you execute first, that all the things that are required for bronze pipelines, then your silver pipelines that would execute things. And maybe the silver pipelines wouldn't have any copy tasks. They would just have notebooks that they wanted to execute. You could actually build a metadata-driven main pipeline that gets a list of pipelines and their parameters to execute. That's more of an advanced thing. So what do these notebooks look like that we're executing? If I've got a staging table that contains a complete a range of data for a range of dates, let's say current year sales SQL and past year's sales SQL, anything before January 1st of this year is executed is from that one. Both of these the queries could run the same merge process because they contain a contiguous set of data for the range of dates for a certain column. So I have a common function merge by date range in a shared notebook, the common Lakehouse merge notebook. And I have a notebook called merge sales that all it does is call the merge by date range for the staging.sales table as the staging table, dw.sales as the target table, and then the date range replace column order date. If I need to use like a natural key or a business key, so sales details, I don't have a range of dates within the table that I can delete and recreate. Then I'm going to have a different one, which is maybe a merge, I would call a merge upsert. And the merge upsert notebook takes a staging table, a target table, and a key column to join on, and any rows that are match that between the staging and the target table match on that key column, they would be replaced. Any columns or any rows in the staging table that aren't in the target table would be inserted. So that would be an upsert. So here's some of the date range, and this is some Python PySpark code that gets a data frame from the source and target tables. And the first top 7 through 15 checks for the existence of the target table. If the target table doesn't exist, then we're just going to take the source table and write it out as the target table. Take the content of that and overwrite that one. If it does exist, then I'm going to get the minimum and maximum values of that range column from the source table and build a replace where clause where that column in the target is between that minimum and maximum date, and then overwrite and specify the replace where. And then there's some magic down there for the merge schema so that the new schema of the staging table is used. So this saves a lot of time. On the merge upsert, it's a little bit different. The first part of it is the same. I'm checking to see if if it doesn't exist, then I'm going to just save it as the target table. So I've omitted that code. And then the bottom section is the upsert part. And I am using a Delta table object in this case, getting the path of that table from the Lakehouse and opening it as a Delta table object, which supports this merge method at line 27. And the merge has an on clause for the source, the key column that has to be the same name in both of those things. And then when matched, update all, when not matched, insert. And there's also an option to when not matched by source, then delete. That one's a pretty dangerous one to use because if you're only loading incrementally, delete all of those other things that weren't in the staging table, which is probably not what you want. So I will just want to briefly show the Lakehouse files. So here's my demo Lakehouse, and here's an example of a JSON file that I'm calling. So this is my daily JSON. I'm going to load my products, customers, the date, current year sales, and current year sales details. And these ones are just overwriting the table in the DW schema for each of these. So these are basically type 1 slowly changing dimensions. We're just overwriting that each time. And the same with the date table. But the current year sales and the current year sales details are going into a staging table, and then there's the merge notebook that we call there. Okay, in light of the time, I'm going to go and just kind of reiterate how we handle ETL requirements or changing ETL requirements. A lot of it, it's very, and this table is what I showed you earlier. In the SSIS approach, you'd have to deploy for any of these, build and deploy for all of these things. But in the Fabric approach, a lot of it is driven by the metadata in those files.
A big thank you to Mike for sharing his wealth of knowledge on metadata-driven approaches. Your insights on streamlining data pipelines in Microsoft Fabric were really invaluable today. Before everybody goes, I'm excited to let you know about our next talk coming up on March 19th at 12 p.m. Central Time. We'll be exploring visualizing the complex, a delicate balance of trade-offs where we'll be navigating the challenges of creating effective data visualizations and helping you determine the right balance between flexibility, cost, and implementation of your specific needs. And we'll have a panel discussion for that. Sign up now at our website to reserve your spot. Thanks everybody for being here, part of our Improving Talk series, and we hope to see you next time. Have a wonderful day.